Hello everyone, and thank you for coming to this flash presentation. I'm Alejandro Perez Alonso, PhD student from IMT Mines Albi A, and today I'm going to present you the synthesis, characterization and application in syngas production with nickel-based catalytic materials. First of all, what is syngas? Syngas is a mixture of two gases, hydrogen and carbon monoxide, that in this case we're producing by the dry reforming of methane. This process is the oxidation of methane by three different oxidants: water, oxygen, and carbon dioxide. The reforming of methane is a widely studied process, which of course needs a catalyst. The best reported catalysts are the noble-based catalysts, but of course these materials are expensive and non-abundant, so they are not optimal from an industrial point of view. On the other hand, nickel, that's a cheaper and more abundant metal, has been widely reported as a good replacement for this noble metal-based catalyst. The problem is that nickel presents a series of drawbacks: lower performance, fast activation, easy oxidation, that we need to overcome in order to optimize this catalyst. Our approach for overcoming these drawbacks will be the preparation of nickel-based catalyst with a small active site. Lately, in the literature, it has been reported that the small active sites present better activity and lower the activation. Consequently, our idea is to prepare small and well-dispersed nickel nanoparticles under 5 nanometers. For the preparation of these materials, a collaboration with the Laboratoire de Recherche Fondamentale Appliquée in Toulouse, where I'm preparing these materials, and who have an experience on the preparation of small nickel nanoparticles in solution, has been done. The challenge was to mobilize nickel nanoparticles into supports. For the preparation of these nanomaterials, an organometallic approach was followed, starting from nickel bicyclooctadiene and reducing this ligand with hydrogen, thus releasing nickel atoms, which forms clusters that will be stabilized by a stabilizing agent, or in some cases the same support that acts as a stabilizer. These clusters, once stabilized, will be absorbed into our support, ending up with our catalytic materials. Two supports-based family of materials have been prepared so far. One based with hydroxyapatite, a calcium phosphate mineral, and another one based in halloysite and nanoclay. With the halloysite-based materials, a screening of different stabilizers, steric, electrostatic, a ligand, and the same support without any additional stabilizer was performed, arriving to the conclusion that the ligand, kinetin in this case, was the best stabilizer. Besides, the ICP analysis confirmed us that the nickel was indeed properly absorbed. On the case of hydroxyapatite, the same support could act as a stabilizer, giving similar results to the kinetin-stabilized particles. On the production of syngas, an initial screening is being performed. So far, hydroxyapatite-based catalyst prepared by this new strategy has been tested and compared with the nickel-based catalyst prepared by the impregnation method. One of the most common used methods for preparing this catalyst, in which it's difficult to control the particle size and homogeneity of our active site. Our catalysts exhibit a higher performance with a methane conversion up to 90% and with a stability over the initial 72 hours, while the catalyst prepared by the impregnation method had a lower activity and started activating after 50 hours. Furthermore, the carbon dioxide conversion showed a similar trend than the methane conversion, with a higher performance of the catalyst prepared by this new strategy. And this is my presentation, and thank you for your attention.